Okay, 2019, restricted answer question 3. It's one of the 3 markers. Okay, melting point of non-metal elements depends on structure and bonding. Using your knowledge of chemistry, comment on this statement. Okay, so actually I probably should have just pulled in the non-metal section. Okay, so I'm looking for everything right of this line. I think there's a lot of data in here, and I think you can use quite a lot of information to make your life kind of easier about it. Try and break it down. So what we're trying to talk about is the melting point, and then we're trying to relate it to 2 different things: structure and bonding. So what you're going to have to do is to pull some information from here to get your melting points, which is helpful. Okay, put some real numbers in, and then you're going to talk about your structure. Now your structures are, in this one we want to talk about monatomics. So if you talk about monatomics in terms of just size, it's an individual atom, so that's going to make a difference just purely because as things get bigger, they're heavier. There is a tiny bit of that. But what you can then talk about in terms of bonding is to link that to London dispersion forces, being the only ones that are going to be part of that one. Okay, right, you then need to recognise your discrete molecular covalent. Let me just get a colour for this one. Right, okay, so our discrete molecular covalent, we are looking at our normal diatomics, hydrogen over here, and we're also looking at the 2 new ones that you know something about, which are phosphorus and sulfur. Okay, so knowing these ones, because this is phosphorus is P4 and sulfur is S8, and obviously all your diatomics are 2. Okay, so you can talk about size in this one in particular. Going the phosphorus to sulfur jump is quite nice because you're going, say, the 4 to 8, you get more of a jump than you would expect. Going from one to the next one, it's not a massive change in size of element, but because you've got the size and the molecule changing so drastically, that's going to make a difference. That would be a nice one to put in. What you also can discuss, apart from just increasing size in that, is now to recognise that you also add in, for all of these, we add in London dispersion forces, and that increases with number of electrons. So again, you can talk about the sizes of that. Okay, and then your last one that we need to discuss is these 3. Now actually carbon can also be in this one because we have discrete molecular covalent forms of carbon. Your fullerenes, C60 being your kind of most common one. But in these 3, that little triangle here, what we now have is network covalent. And what we're looking for that recognition is that for it to melt, what you're having to do is to break internal covalent bonds, which are super strong, and you have to break all of them because they're all connected for you to get to the point where it can freely move around. So that's why they are so high. So I think you can actually split it into 3 parts. You can do monatomics and explain what's going on with that and with their LDFs. You can talk about discrete molecular covalents and talk about the internal structure in terms of size of molecule, and then LDFs. And then you can also talk about network covalents in terms of their structure, and then how that bonding in terms of covalence increases the melting point. If you split it up into that, you are obviously, nicely giving 3 kind of sections, and you should certainly be able to pick up quite a few points on that one. Okay.